So hello there and welcome back. The question that we have for today is detect cycle in directed graph. In the previous video we solved the question on detecting a cycle on an undirected graph, and this seems to be a variation of the previous one. So the statement says that given a directed graph with vertices v numbered from 0 to v minus 1 and edges e, check whether it contains any cycle or not. So I'll use one example to demonstrate the difference between how the directed graph and undirected graph can differ in detecting the cycles. So I'll draw an undirected graph like 0 is connected to 1, is connected to 2, is connected to 3, is connected to 4, and then 1 is connected to 5, and 5 is connected to 3. So over here, we clearly can see that there is a cycle over here and there is no problem. So whatever we discussed in the previous video, which was basically to use depth first search to produce a tree for connected graph, and then if a node connects to itself on that produced tree or to one of its ancestor, then we return true as the cycle detected, else we return false. So that was the basic approach that we came up with for undirected graph. But for directed graph, the difference that we will face is if I were to say 0 is connected to 1, now this time it's directed, and 1 is connected to 2, 2 is connected to 3, 3 is connected to 4, and then 1 is connected to 5, and 5 is connected to 3. And it will seem like again we have a cycle over here, over right here. It seems like there is a cycle, but it is actually not, because you cannot cycle in the loop 1 2 3 5. You can go from 1 to 2, you can go from 2 to 3, but you cannot go to 5. Or if you were to go from 1 to 5, 5 to 3, you cannot go to 2 and then again back to 1. It's directed, you cannot travel here, and therefore this is not a loop like this. It's not a loop. uh, this way the loop is not possible. And similarly, if you were to try this way, you can go from 1 to 2, 2 to 3. I'll just change the color, pardon. So if you were to try something like a clockwise loop, again you can go from 1 to 2, you can go from 2 to 3, but this is not possible, and this is not possible, and therefore this is not a cycle. So now we understand the difference between detecting a cycle in a directed graph and in an undirected graph. So again, for a quick recap, what the approach is going to be is the fact that we know for sure is the interesting fact that we will again take advantage of is, it's worth noting again that DFS produces a tree, and as we mentioned earlier, it's a tree, not a binary tree. So DFS produces a tree for connected graphs. This one is a connected graph. This is a not connected graph. So just to clear the analogy on connected graphs. So we have this fact that DFS produces a tree for connected graphs, and if something produces a tree, then we got to have the ancestors and children, right? So let's take this as an example. What will happen is 0 will go to 1 when we are doing depth first. Then we either can go to 5 or 2. Let's choose 2. So we go from 1 to 2, then 1 to 3, and then 3 to 4, and there is no way more, so we come back to 3, no choice, come back to 2, no choice, come back to 1. But from 1 we have choice to go to 5, and from 5 we have choice to 3. And the basic idea is to that, like, visited is used as a set to keep track of visited nodes. And what the basic change in our code, what we are going to do is we are going to develop a scene variable which will be also a set, and its job will be pretty similar to visited, but when we come back from a vertex, like when we reached 4, we are going to get back to 3, right? So what I'm going to do is I'm going to pop 4 from scene. Rest up till now, when we are tree traversing the graph, what I'm doing is the role of scene is exactly the same as visited. But when I am coming backwards, when I'm exhausted from 4, there is no way I can go, so I come back to 3, right? That happens through a recursion call. The recursion gets over, so I get come back to the previous recursion stack. So the moment I'm returning, what I want to do is I want to pop from scene. So in the visited, there is no pop, never popping, never a pop operation. But here we will pop when we reach a node from where we cannot go any further. And the advantage will be, if we were to use visited, what will happen is when we come from the route 1 to 5 and then 5 to 3, 3 will already be a visited node, right? Because we visited it using the path 0, 1, 3, 4. So for the tree, it will be like we met someone already visited. So it will say 3 is an ancestor. It will act like that if we are supposed to use that analogy that everything in the visited is an ancestor. But actually, 3 is not an ancestor. So how do we do that? The way is that when we go from 1 to 2, 2 to 3, 3 to 4, when we are coming back, we are popping out uh, the node from a similar set that we developed by the name scene, and that we will use to match our ancestor. So when I go back to 2, I have popped 3, and now 3 is no longer in scene. And I come back to 1, now 2 is also no longer in scene. So if 5 I connect to 3, 3 is a new node in scene, therefore there is um, no clash of ancestor. And uh, also 3 is in the visited, so we will use that information to avoid unnecessary repetition of the traversals. So I hope by this point, theoretically, you are somewhat clear. I believe there is not clear clarity, but now I'm going to shift to my editor and I'm going to use this example, and so I can actually implement the code for this problem and use the visited and seen variables. And when I will be doing it, actually, I believe it will make a lot of sense and the entire clarity will be there. So let's switch to the editor. So here on editor, I have the entire example set up with 6 vertices and 6 nodes and the edges in ADJ list, adjacency list, as per the example that we saw on the whiteboard. Detect cycle is the function that we are going to code. So let's start. So first of all, I'll initialize our answer variable. I'll name it as cycle detected and I'll initialize it to false. I do this inside an array. I'm doing this inside an array because in Python that will give this variable a more wider namespace so that I'll be able to use it in the functions that I'll define inside this function. So basically it will make this variable a globally accessible variable or a global variable. Now I'll also define my visited variable and it will be for now an empty set, and followed by a seen variable which will be also an empty set. A function that will perform the depth first search I'll pass for now. We will develop this later, and then I'll be iterating over all the vertices of the graph. So this is necessary in case of unconnected, non-connected graphs. So if I find a vertex that has not been visited, I'll do the depth first search on it. So if the vertex is not visited, I'll do the depth first search DFSV. And also, if after the depth first search I see that the cycle was detected, that is cycle detected equal to true, what I will do is I'll return or break the loop, and at the bottom I'll return the answer. That is, our answer is cycle detected and the zeroth element because it is in the form of an array. So this is the base of our solution, which by the way is exactly the same as for it was for the previous question where we were supposed to direct the cycle for an undirected graph. Here the case is for directed graph. However, by for till up till now, up till so far, everything has been exactly the same, other than we have just introduced the scene variable, which is a set, and we haven't used it anywhere. We have just declared it. So let's proceed with programming or coding the DFS function. So I'll remove the pass now and we'll put the actual code here. So first of all, I'll insert the base condition, that is, I don't want to do depth first search at all if I have already detected a cycle. Then the typical depth first search, that is, I want to add vertex to visited, and since we also have the scene variable, I want to also add it to scene set. So now I will iterate over the neighbors of the vertex v. So to do that, we have the line for an in adjacency of v. Then I want to check that if the neighbor is in visited or not. So if an is not in visited, so this is a new node. I want to perform the depth first search. That is the make the recursion call. So I'll simply do dfs n. Also, else if, so if n is not in visited and n is in scene, so that is, if n is in scene, what I want to do is I want to simply set the flag for detected cycle as true and return. And I'll return. Now if I will run this code, it will give me a false output, that is wrong output. Let me show you. So I'll just run this code and we expect a false, and this code will return, it returns, wait for a while. Okay, it is returning an error. So there's a problem. I have used the function name by mistake. It should have been cycle detected, not detect cycle, the name of a function. So it should have been cycle detected. Now I'll run the program and it gives us true. So now what is exactly happening? What is happening is visited by now this code in this code, visited and seen are exactly the same copies. I have initialized them as empty sets, and then I add vertex to visited. At the same time, in the just next line, I also add to seen. So visited is nothing but the exact same scene set. And what I'm doing in the neighbors iteration is that if n is not visited, visited is the same as seen now, right? So if n is not in visited, what I want to do is I want to do depth first search, and if it is in visited or seen, which are by far now the same copies. So if it is in the visited, I am setting that yes, I've detected a cycle, that is there is a node that connected to the ancestor. But that's not the case. Not every element in the visited is actually an ancestor, and that to overcome that, the entire idea was to therefore introduce scene. And scene has to be slightly different from visited, because when we are getting back from the recursion, we are getting back on the stack when there is no way further for the node to proceed and we are coming back. What we want to do is we want to pop the element or remove the element from scene. So let's do that. After there is no neighbor for the vertex v, that is, we have exhausted all the neighbors for vertex v. The only way is that we are going to go back on the stack or get out of the recursion call. So just before doing that, what I want to do is I want to pop the vertex v from the scene, right? So I'll type here scene.remove v just after we are done with the neighbors loop. And if you will see, that is the last line on the DFS function. So let's run our code now. and there is an error. Okay, so the capital V should have been small because we are dealing with small v. Run, and it returns false, and that is the correct answer, all because of this line. If I comment it out and rerun the code, it will return me, okay, it returns me true, and which is a false answer. So this code doesn't work without this line, and that is the power of using two sets to keep track of ancestors in the depth first search tree being produced by depth first search traversal being done on the graph. Now I'll uncomment this line and run the code, and it will return me the actual correct answer, which is false, because there is no cycle on this directed graph. Now I'd recommend that you take a pause and look at the entire code, all the logics that we used, and let it all sink in. And that is it. Congratulations, well done. This was not an easy question. You deserve a pat on your back. Take a break, have some fresh air, and come back when we can talk about the questions.